In this video, we're going to go through solving a weak acid equilibrium problem. The first step towards solving one of these problems is to draw a sketch of what we expect to see in the beaker. So here we draw our little cartoon of a beaker, and we see that it's a 1 liter solution, so we'll write the volume down here. And now we look to see what's inside the beaker. So according to the problem, we have 0.1 moles of some generic acid HA, so we'll write that, 0.1 moles of HA, and there's also a lot of water. Once we've written down the contents of our beaker, now we can start to predict what kind of equilibrium will take place. It's not always so simple as just looking at the problem. We have to decide which equilibrium is most important. So we know that acid-base reactions are an acid reacting with a base to make a conjugate acid and a conjugate base. So let's identify our acids. Here HA looks to be our acid, so we have HA aqueous, and it reacts with a base. The only base that I see present is water, so we'll look for the strongest base, in that case water. And the conjugate acid will be hydronium ion, and the conjugate base is A-. Once we've identified what is present in solution and the equilibrium, now we can go about solving this problem. Notice we haven't really talked about the fact that the pH of the solution is 4, but that is really consistent with what we predicted about the formation of hydronium. So we've already said that this reaction is HA plus water in equilibrium with hydronium ion and conjugate base. We don't know what K is, but we do know that the expression Q is the activity of hydronium ion times the activity of the conjugate base over the activity of the acid. And so now we can use an ICE table, or an ICE table, as a tool to help us solve this problem. So let's set it up. So HA, hydronium, conjugate base. And instead of going automatically through this, we're going to realize that every cell of this table is actually an important and interesting question we have to solve. So I stands for initial. And so this over here is the initial concentration of HA. So if we go back to the problem, we saw that it's 0.1 moles of HA. Right? We had 0.1 moles of HA in a 1 liter solution. So we start with a 0.1 molar solution of HA. Notice in the ICE table we use molarity, and in the beaker diagram we use number of moles and keep track of the total volume. And this is really important for more complicated problems later on. Okay, next question. What is the initial concentration of A-? Look back at your beaker. Is there any H- in the beaker? There isn't, which means our initial concentration of A- is 0 molar. So the last question in the initial row of the periodic table, in the initial row of the ICE table, is the initial concentration of hydronium. So if we assume that all of this is happening at 25 Celsius, that initial concentration of hydronium is 10 to the minus 7 molar. The reason we keep this is because there will be problems down the line where we will not be able to neglect the autoionization of water, and so this will help us. Traditional ICE tables stop there. I prefer to include one more column, and that's for Q. So let's calculate the value of Q here. So it's 0 times 10 to the minus 7 divided by 0.1, and that's 0. So that's less than K. I don't know what K is, but I know 0 is less than it because K has to be somewhere between 0 and infinity, so it must be that K is bigger, so we don't have enough products. So that leads me to my next row of questions, not next row of answers, my next row of questions. What change will happen? Well, since we know products have to form, we are going to form products. How much? I don't know. Some amount. but the amount that's going to form is going to be stoichiometric, so X amount of hydronium will form, X amount of A- will form, and X amount of HA will be consumed. What are we left with once we reach equilibrium? That's my next row of my ice table. So 0.1 minus X, 10 to the minus 7 plus X, and X. And what's the value of Q once we reach equilibrium? That's K, and since this is an acid, Ka. At this point, we can plug all of this into the expression for Q, and we get that Ka is equal to X times 10 to the minus 7 plus X over 0.1 minus X. Now this looks a little gnarly, especially since we seem to have two variables left. But if you remember, in the original problem, it told us that this solution has pH equals 4 at equilibrium, which means the hydronium ion concentration at equilibrium is 10 to the minus 4 molar, which means that 10 to the minus 7 plus X is equal to 10 to the minus 4, which means this is 3 orders of magnitude difference, that X is 10 to the minus 4. So if we plug that value of X into all of our values over here, we get 0.1 to 1 sig fig, that hasn't changed, 10 to the minus 4, and 10 to the minus 4, which means that Ka will be 10 to the minus 4 times 10 to the minus 4 divided by 0.1, which is 10 to the minus 7 Ka. So let's review. We started off with the premise that this is a weak acid. A weak acid means that some of it reacts, but not all of it. And we get a K value that's not large, but it's also not smaller than Kw, which is the autoionization constant for water. We end up with a substantial amount of hydronium that forms, 3 orders of magnitude more than what we started with. But we have nearly 0% reaction of the original acid. So traditional acid-base problems will usually take this exact same form, where we have an acid reacting with water to make hydronium and conjugate base. So we have some initial concentration of acid. If we're starting at 25 Celsius, we're going to start with a certain amount of hydronium, 10 to the minus 7 molar, and most acid-base problems start with either only acid or base. So some of the acid will be consumed, some products will form, and in the end, we get equilibrium values that look very similar to these. So the question is, what is X? X, this is where all the chemistry takes place. Up until here, a lot of this is algebra, but X, this is the chemistry. So if we're dealing with a strong acid, which strong acid means 100% reaction, then X is equal to the initial concentration of the acid, meaning that all of it, or almost all of it, close to 100% of it, will be consumed. That's the definition of a strong acid. We've talked that there's another type of acid, which is an acid that, despite being acid, is worse than water. What does it mean, worse than water? If I put it in water, it won't lower the pH. That means 0% reaction. So if it's 0% reaction, that means X is equal to 0, and there's not much to really talk about. And then there's our weak acid. Our weak acid, well, now we have to ask ourselves, is X big or is X small? So in the case of comparing it to the initial concentration of acid, weak acids tend not to react very much, and oftentimes we can ignore how much acid is consumed. But given that they are a weak acid and they do change the pH of water, we can also usually ignore the autoionization of water. And this is usually. There are exceptions to these rules. For example, dilute acids, or where the Ka is starting to be similar to Kw. In that case, we can't always make these approximations. The good thing you can do at the end of every problem like this is you can check. If you see that your final concentration of hydronium is 10 to the minus 6 molar, assuming that X is much, much greater than 10 to the minus 7 is not true, because they're within 10%. So this is a good paradigm for solving acid-base problems or weak acid problems. Hope you found it useful.